challenge the Gadigal people of the Eora Nation, the lands that we are meeting on today. We're from Brisbane, so we're generally in the Turrbal or Yurrugal nations as well up there in Meanjin. And of course, even though we're talking nutrient and systems and circular economy, we kind of have to sort of start somewhere, I suppose. And this session's about where we might start in actually collecting the urine, which raises lots of different issues. So I've got some great speakers today. And the first one is Stefano Freguia and Ligao. Ligau's from South East Water, Stefano's University of Melbourne, and you're also the co-director of the Nice Hub, aren't you?
Deputy.
Deputy.
Yeah.
Yes, deputy. And you're going to be talking about downstream effects of urine and its conversion to liquid fertilisers. So please welcome Stefano and Lee.
Thanks, Stefano. Great to be here. And I'm not coming along. So Ligao from Southeast Water, our main industry partner, and my PhD student Chen here, because obviously I will just need his help on some of the items here, so he knows the stuff better than me. So it's great to be here, and this talk is really not linked to one of the three nodes. It's more broad nature. So Abraham mentioned how he found fertile ground in Vermont for urine collection and treatment. In Australia, we've been focusing on cities more than rural areas. So when we look at Australian cities, we already have sewers. And so one of the questions that came up from the beginning is what happens when you take urine out of sewers to the sewer and the sewage treatment plant downstream. So we have been looking at this for quite some time, in fact, and the idea is that urine contains the majority of the nutrients. We know that, NPK, but also sulfur, 70% of the sulfur, and sulfur is what causes sewer corrosion. So we're looking into that, particularly looking at this right-hand side box, the problems with current sewage system. In Australia, sewage systems are coming to age. They're facing replacement or upgrades. And so what's the smartest thing we can do when we now have the opportunity to work with reduced nutrient loads into our sewer system? So what we are looking at in this project is two separate lines. First is these downstream effects of taking urine out of sewers. And second, together with Southeast Water, we wanted to look at yet another technology. So we're really technology focused. We want to be comprehensive in the NICE hub. And so we're looking at membrane distillation coupled with MBR. We're looking at electrodialysis or microbially boosted electrodialysis in the Brisbane node. We kind of needed to look at RO as well. So this is what they're looking at in South Africa and in the US. So we wanted to have our spin onto the RO story, and that's why we're looking at it as part of this project. So, two sides of the story, looking at downstream effects of urine separation, and two, RO for urine concentration. So this actually started with urban utilities before NICE, when we were really interested in kind of estimating what are the effects of this urine separation. So we modeled it. So we modeled it with the Sharman UQ using a well-established sewer model. And the model told us if you take 75% of the urine out, you will actually experience a slightly decreased sewer corrosion, but not major. But when we look at sewage treatment plants, the model told us if you need to upgrade these treatment plants from where we are at now to an increased capacity, what the cost of these upgrades is going to be greatly diminished if we are diverting out a fraction of the urine. So this is just one of the graphs that we have in a paper published in the journal Hazardous Material together with our industry partners. And it shows, for example, if you look at the middle column in the graph on the right-hand side, that if we're going from a 1 million to 1.5 million equivalent population size upgrade, the cost of that upgrade is going to go down from $130 million to about $30 million because of the benefits, the reduced size of the bioreactors and the reduced energy consumption that goes into treatment. So this is pretty major, and this leads into that value chain that we have been talking about. What can we actually use as the value proposition? It's exactly what Abraham was talking about, but in this case applied to a large city with a developed sewer system. But the question was, are we happy with the model? Of course not. The model is hugely simplified and sewage is highly complex. So we don't really fully trust it, or we do trust it, but we want to validate it. So we're going to validate it both in the lab and in the field. It's going to be really hard to do it in the field, but I'll show you in a minute how we plan to do it. So SBR setup. This is what Chen set up in the lab to simulate a sewage treatment plant with a sequencing batch reactor with a few different stages. So you load it up, you have anoxic and aerobic cycle a few times, and then you have a settling phase and a decant. So basically in one vessel, what happens in a sewage treatment plant. And we want to feed this system with stuff that looks like sewage. We can't really use real sewage because then we don't know how to take the urine out. We don't really have sewage that is being created without urine, because although we have waterless urinals and urine diverting toilets, they all discharge into sewers that already have a flow going. So Chen came up with some formulas to create his own sewage, and the influent here shows chemical oxygen demand, suspended solid, ammonia. Can you tell us a bit about what you put in there to make it look like real sewage, Chen?
So basically, we know that our sewage contains greywater, urines, and brown water. So our sewage was formulated and manufactured based on this formula. For example, like 74% greywater, 24% of brown water, and 1% of urine. So for the table that show here is the performance SPR that cultivate without urine diversion. So after the conference and summit, we will start the urine diversion, and we will observe the impact of urine diversion to the performance SPR. So how we do this is we will gradually reduce the composition of urine. For example, we know that 1% of urine in our sewage, so we reduce to 0.75%, 0.55%, 0.25%, and totally no urine. So we will observe the performance of SPR.
Thank you, Chen. The other thing that Chen is planning to do is to build a simulated sewer pipe in the lab to load it with the same stuff based on synthetic ingredients and see what happens in the sewer, where we expect to observe a decreased amount of hydrogen sulfide in the headspace of gravity sewers, and we expect a decreased formation of hydrogen sulfide in the rising main based on the modeling. But what we know is that also the pH gets affected, and there's cascading effects that are not so clear. We might have less fermentation happening, we may have less conversion of slowly biodegradable to readily biodegradable COD. So the influence of a treatment plant might look really different, and it might not work the same way as it does today. So that's what we plan to look at in this objective, which is going to happen a little bit later. Maybe it will get started by the next NICE summit. So, Lee, how are we going to look at this exact problem in a real sewer system? So, with real sewage. Actually, what we have is the perfect opportunity in Melbourne to do this. So we have a new campus coming up in Fisherman's Bend, and this campus is going to be completed in 2026, and with a lot of effort we managed to almost convince the developers and our leadership in the university to include urine diversion in one building. This full building will also be serviced by its own small sewage treatment plant based on MBR and RO. This will enable a lot of research opportunities, but this will also become the first place in the world, I believe, where we could test the effect of urine diversion on sewage treatment, because this whole building will be serviced by its own little sewage treatment plant. So if you want to join us to do any testing of how a sewage treatment system forms in a urine diverted system, this is going to be the place to do it. But it's going to be legacy of NICE, because it's going to be started after the end of NICE. But this also helps us to look optimistically into the future. This idea is not going to be over at the end of NICE. It's going to be commercial technologies, commercial fertilizers, and this place that we can use for many years to come to do more testing. So we're kind of running out of time, but I want to show also this reverse osmosis. Actually, Lee, would you want to talk about your involvement in Southeast Water's involvement in Fisherman's Bend? So Fisherman's Bend, actually, this new campus falls within the catchment of Southeast Water.
I guess just to very briefly mention about our involvement. Like Stefano already mentioned, the two key components of the project is about the downstream impacts for the urine separation, and secondly is about new technology to recover the nutrients or recover the resources from the urine. So basically we get this, we call once in a generation opportunity to implement it at Fisherman Bend. Just a bit background of Fisherman Bend. Fisherman Bend is an area of more than 480 hectares, just right to the city center of Melbourne. And this is the biggest urban redevelopment in Australia. And we have 5 precincts with education precincts, industry precincts, and residential precincts. And like Stefan already mentioned, we will have Melbourne Uni's new campus here. So we are going to implement a lot of new innovations, integrated water management approach, resource recovery, circular economy method, try to bring the new innovations to our customers and build the most available communities here. So that's probably, I guess, the mention. Thank you.
Thanks, Lee. So for the RO system in the lab, so this slide shows that we put raw hydrolyzed urine in. So most people use acidification or use fresh urine. You use hydrolyzed urine to be different, and also because that's the easiest thing you can get, because urine hydrolyzes almost instantly. And we managed to get, as expected, very good recoveries of NPK, with N being the worst because it goes through the RO membrane to some extent. So this technology is pretty good for phosphorus recovery and concentration up to a factor of 4 times. So high pK recovery, low energy consumption estimated only at this stage, about 1 kilowatt-hour per kilogram nitrogen. We need to always keep energy in mind. What we found was minimal biofouling. I initially wrote no biofouling, that Chen corrected me and said to put minimal because we did find some cells there, but pretty much the membrane looks like a clean slate. And that's because ammonia is biocidal. Actually, ammonia is used to clean our membranes. So we actually don't need to do any cleaning because it happens by itself. Although we have a little bit of inorganic scaling, and that still causes a flux decrease, but that's readily reversed with a bit of an acid wash. And then the other thing, inability to separate nutrients from micropollutants. We're learning today that that might not be an issue, which is really good news. So, if that's the case, then we don't need any pretreatment. But if we do need pretreatment, we'll be prepared to implement one. In fact, because I brought up the question of sodium before, do you know what happens to the sodium here? Does it go through the membrane just like P&K, or?
No, the sodium will be recirculated and retained in the retentive. So the sodium concentration will be pretty high in our case.
Okay, so sodium remains a problem. Okay, so this might go into the nice loo if we feel that it's going to be good enough. Thank you.
Just like
No, it's, we pull out, it's finished. So, thanks for your attention.
Thank you, Stefano and G and Lee. We're waiting for questions after the session, so there'll be 2 more presentations around 10 minutes, and then we can, so hold on to your questions, write some notes, and then we can